Turn it over to Vincent Chevrier from the Spatial Planetary Sciences Center.
Thank you, and good afternoon, and thank you very much for having me. So yeah, I hope I'm not going to be too divergent for you. So my area of research is also very interdisciplinary, but not in the sense that I've heard so far. It's actually I'm much more in the hard science side, as I think I've heard it called. So I was trying to find a title that would resonate with a lot of people and try to get you a sense of what I'm doing. And I thought habitability in the solar system, that sounds about right, and that really sounds kind of nice, very sci-fi. But actually, it's very well defined. It's actually a NASA definition that you can find on the website for the NASA program for habitability research, or habitable worlds. So by saying habitability of the solar system, I was already very restrictive. So it's investigate the synthesis and chemical evolution towards complex organic systems in planetary environment over long time scales. Good luck with that. But if you start to try to refine a little bit, habitability connects geology, chemistry, and biology. So which I've tried to summarize. I've seen a very nice triangular diagram this morning, so I thought I was going to show you mine. So most of the time, it's going to converge liquid stability and formation. You need to have habitability to have life. You need a liquid to allow all chemical reactions to occur. You need an energy source. And you need organics. And for example, at the cross between those three type of resources or environment, you're going to find what's called the spatial region. That's how we define them on Mars. So, and of course, habitability is going to widely vary depending on the planet you consider and even what type of biological environment you want to consider as well. That's why there is a lot of studies performed by NASA and also by terrestrial biologists about extreme environments. Try to understand the extrema of life to apply it eventually to other planetary environments. So I'm mentioning here ocean worlds and Titan. And of course, I'll go back on that if I have time at the very end. It's extremely important for exoplanets research. All right, so what I'm going to focus on, as I showed previously, is Mars in that grand ID. So here are some the main properties of at the surface of Mars. You want to deal with habitability, is what you're going to have to deal with. There is virtually no organics identified, despite most extreme efforts by NASA, by ESA. We virtually have zero trace of organics at the surface of Mars. Virtually, that doesn't mean it's completely deprived, but it's really close to the detection limits of the instruments. That's one of the major issues that we're dealing with. Number two, it's very limited liquid. So I showed you here one of the main observation of potential liquid flows, which is called RSLs for recurring slope linear. So those flow features that were identified several years ago, and NASA made a huge claim. We found water on Mars. You may remember that. It was around 2015. No, they didn't. I'm sorry. and don't worry, I'm not the only one. And that's all my work is about water on Mars. So in terms of shooting yourself in the foot, that's perfect. But no, it's not liquid water flowing. It's probably a dry flow, but that could be initiated by water phase change. So liquefaction of water. That's still a very high possibility. So why? Because water is still pretty cold. On average, it's 220 Kelvin, so it's very cold, but it has very large diurnal temperature variations. So you could reach the point where you could melt some water ice, or especially if you're in the presence of salts. And that's what I will show you in a couple of minutes. because that's what my work is about, trying to understand the effect of salts on the stability of liquid water on Mars. So there are other candidates, as I was saying. Mars is not the only one. It's one of the NASA's favorite, but it's not the only one. So you have Titan, which on the opposite side of the spectrum is extremely rich in organics, but extraordinarily cold, around 90 K. So cold that at those temperatures, you're only dealing with liquid methane or liquid ethane. So when you want to study habitability on Titan, which I do as well, you try to understand what can happen in liquids that are totally exotic, totally irrelevant to Earth. So it's an entirely new type of chemistry that you're trying to understand. Other possibilities are, for example, Europa and Enceladus, which are quoted as ocean worlds because they have very thick ice crust, and beneath that ice crust, you should be able to find a giant subsurface ocean. But well, when you have an ocean, is a very good environment to develop life. That's why those planetary bodies are excellent targets to go study the possibility of life or of prebiotic chemistry. The problem that you're dealing with is that you have about 10 to 100 kilometers of ice separating you from the ocean. So it's all indirect observations. And those would be powered by tidal heating, so the deformation due to tides when the moon orbits its own planets, that is Saturn or Jupiter. So now I can show you maps. And I apologize because compared to, I feel almost ashamed, compared to like the sheer volume of data that you are dealing with. I heard like tens of petabytes. I mean, if I'm dealing with gigabytes, I'm like, wow, that's huge. So it's much smaller volumes of data. And I try to show a few of the problems that we're dealing with. So, for example, we have, on Mars, we have maps of distribution of subsurface water ice using a gamma ray spectrometer. So you can see here you have the volume of ice in the surface soil or the regolith that can go in the polar latitude up to more than 50% ice. And other maps using other instruments have shown, for example, here you have the distribution of silicates and here the distribution of red dust on Mars. So we have those kind of chemical and mineralogical maps. We tried more or less successfully to define habitable regions, but it's not really, it's more like let's compare two maps together and see which one looks better. So here that's a map that shows the boundaries for different types of ice distribution, and I'm not going to go into the detail of that, just to show you that it's very crude. It's very low resolution. It's not really, I would say it's not really well done. And what I've been trying to do, for example, is that kind of work. I know the pixels are huge, and I'll tell you why in a second. That shows the stability of a liquid brine in percent time of the year. So you can see it's not a lot. It's very small for a compound that's called calcium perchlorate, which is a salt that can form a very low temperature liquid. And it's kind of like the best case scenario. So it shows that at high latitudes on Mars, you should be able to form liquid brines for a very small fraction of the year. So even if we can get to liquids on Mars, it's always going to be very small amounts. And that's been done using a global circulation model. So a model that calculates the meteorology at the surface of Mars, and we inject that into a thermodynamic code, and then we try to map that. And ideally, what you would want to do, for example, is compare that kind of map, which is theoretically, numerically calculated, with that kind of map, which tells you here is where we saw ice distributed. And that's often the kind of limitations I personally run into, because it's not that easy to compare all those multi-layered. I know, but probably for you it sounds super that kind of self-evident, because after that you can compare to each other, and I'm like, wow, I'm swimming in a nightmare with only two. But that's often the kind of issues that we are running into. But that's the essential of the type of work I do, is try to map the distribution of liquid brines and liquid water and different types of processes affecting liquids at the surface of Mars. Okay, so why is it? I was talking to you about exoplanets. Yes, because the type of work that we're doing at the scale of the solar system is already being applicable to exoplanets. With the recent increases in detection limits, we can detect smaller and smaller planets, down to almost Earth-sized. So there is already a catalog of potentially habitable exoplanets. And I don't know if some of you have ever heard about that Drake equation. That was an equation designed in the 60s to define the possibility of finding extraterrestrial intelligence. So, okay, now we're in the realm of sci-fi, but it's not entirely anything beyond that term. So here you have the rate of formation of stars and the fraction of those stars with planetary systems and the number of planets per solar system with an environment suitable for life. And then the rest is more about intelligent life. So let's forget about that part. But all that part is pretty much the fraction of potentially habitable planetary systems, which is very interesting and important for future exploration by NASA. And especially when we're going to have the James Webb Telescope, which is going to be able to do extremely high resolution observation of planetary environments, we want to understand what makes a planet habitable and how can we detect it. And that's one part. And the second part, which might be a bit closer to home for you, is, of course, human exploration. If you want to send humans on the moon, or you want to send humans to Mars, you need to understand what resources you're susceptible to find and where they're located and how to extract them. So I uploaded a couple, and that's my last slide. So for example, you might have heard about those plumes of methane on the surface of Mars that have been identified a couple of times at very small concentrations in the atmosphere. But it's still pointing to the possibility of having much larger deposits in the subsurface. And methane is an extremely valuable energy source when you're on your own at the surface of Mars. And the other one is the distribution, for example, of water ice at the south pole of the moon. And of course, water is the most important resource that you can expect to find at any planetary surface. So there is a lot of work we're trying to do in terms of mapping resources and their stability at the surface of planets. All right, thank you.